Hello, fam. I thought I'd talk a little bit about Earth in terms of its shape and having a spherical, relationship and physical property to it and value to it, and also having a flat relationship and flat value to it. And maybe this video has been a long time coming. I probably would like to go into have a thorough discussion, but I thought I would have a brief one as well. And part of me has also avoided it in the sense that there's a wealth of historic information here and also new information as well. Okay, so I was born and raised in Brooklyn, New York, the Northern Hemisphere, and there are cool ways. I by no means am I an expert at the stars, astrology, the night sky, anything like that. But there are some things that are kind of, if you wanted to have fun with it, kind of universal in a sense. For everyone who's in the Northern Hemisphere, generally speaking, or anyone who has a little bit of interest in science or even a little bit of interest in the sky and whatnot, you know the North Star, Polaris. You know about that. And it's because it's such a consistent star. And also because of its relation to the North Pole and stuff like that, so it's really cool to know. And it's also pretty bright, or at least noticeable. And we used to always love to say, people say, oh, it's the brightest star, but we used to always love to roll off a little cool fun fact, which is actually it's not the brightest star. In fact, there's a whole bunch of stars that are brighter than the North Star and stuff. So we used to always love to that. So we know the North Star, and there are two other things at least that are well known. Okay, very cliche for the general person looking at the sky in the Northern Hemisphere and stuff, and that's the Big Dipper and the Small Dipper. If you just wanted to roll off any cool little idle facts, or you're just hanging out having a good time, not trying to be pretentious or whatever, and you're looking up in the sky in the Northern Hemisphere, okay, boom, right away you say, well, there's the Big Dipper, there's the Little Dipper. I mean, and it's cool, and it's definitely such a fun way to get yourself started, and then usually you'd love to roll off that little bit. Well, do you know the Big Dipper and the Little Dip? They're not constellations. They're not actually constellations. They're part of. So you always rolled off that little one when you wanted to sound like, well, I know a little bit, and it's not really hard to remember to roll and have some fun facts to get people interested. Oh, well, the Big Dipper is part of Ursa Major, and the Little Dipper is part of Ursa Minor. Okay, and those are the constellations and stuff like that. And the importance about these constellations and the importance about the Big Dipper is it has a whole heap of significant stars in the Ursa Major constellation and stuff like that. Okay, so you knew that. And I mean, and in these things, if you're into it or even a little bit, they become very connected to you. Not in a really, but just normally speaking, when you're looking up and in any idle time or having free time, these are the things you always, the Big Dipper, the Little Dipper, man. It's like, and the North Star. And then occasionally when Mars or something was visible, and you say, well, that's not a star, that's actually Mars. You know what I mean? We love to say these classic. Okay, well, in a little more than 10 years ago, right, I migrated to the Southern Hemisphere, the beautiful, legendary Southern Hemisphere. Okay, so that's where I am now. I'm in Australia. If you guys didn't know, I'm here in Australia, Sydney, Australia. It's beautiful, amazing, great place. And but I truly believe there are great places all over the world. This is definitely one of them. I totally made a mental note. I didn't make a big deal about it, but I totally made a mental note. I said, wow, I'm going on the other side of the world. I thought I had fun saying it. It's like I'm in the Southern Hemisphere. Like spiritually, and thinking in terms of that history and the lineages and stuff like that. There's certain things we share, and then there's certain uniqueness and stuff. That doesn't make us different, but there's certain uniqueness. The Southern Hemisphere, Honestly, guys, I mean, if you want to follow that, I mean, the Southern Hemisphere has a lot of great origin relationships, especially in this third or fourth phase of great human civilizations on the planet and stuff like that. The Southern Hemisphere, I mean, come on, you know what I mean? But the Northern Hemisphere, you still got some stuff there too, and honestly, there was peoples all over and stuff. But so yes, so to make a long story short, when I got here, okay, I looked up at the sky. I made sure to start to observe and see what's going on and just get a feel for it. And it's cool because there were heaps of stars and heaps of constellations, things that I wasn't used to, okay? And yeah, So that was one. And another thing which occasionally I thought about in perspective, or a term that in perspective in my mind is like, wow, I don't see the North Star anymore. That's gone. The North Star is gone. I don't get to see the North Star anymore. That's not my reality anymore and stuff. So, wow, very interesting, right? So let's see what's happening here. Because, okay, if the Earth was flat, no matter where I went on the Earth, okay, the sky, okay, should be pretty constant. Even if you're spinning this way, still constant. I should have access to all of the stars that we have access to. Everyone should, okay? So, you know what I'm saying? You know what I'm saying? So wherever you are, wherever you want to go, you should have access to that stuff, okay? But this is why we have such a thing as an equator. Our ancestors did brilliant work on this. They were so into this that it's incredible how into this they were. It's incredible how precise that they were able to do certain things, how they can put stones and how they could build things to such relationships in geometry aligned with the stars. It's incredible because they understood all this stuff. They understood the relationships. They understood all these relationships. They understood that the Earth was a sphere and it wasn't flat. Okay, so, all right. So when I went from the Northern Hemisphere, when I went over to the Southern Hemisphere, the North Star was gone. The North Star was gone for me and stuff. I swapped one for the Southern Star, so over here, in case you didn't know or you're unfamiliar with it, our legendary one or whatever for the South Pole and stuff like that, and our legendary little star is the Southern Cross or the Southern Crux, okay? And that's about 4 stars or something like that, and it makes like a cross and stuff, sort of like the way you would do and we always symbolize it in a kite. And in generally speaking, it's on the Australian flag because we know how important it is. We know how significant it is. Like deep down inside, these were the equivalent of advanced knowledge. It still is actually, and there certainly is an agenda to take you away from it. But it isn't an agenda necessarily shared by everyone. But there are particular agendas, of course, that seek to make this privilege to understand these things. And the fact that flat Earth has gained such momentum like that for a while, whatever, certainly proves their point that they will make accurate knowledge, a privilege and rare. And like it was once upon a time, where only royalty and special resources were able to read and write and stuff, and everyone else was in the dark. Okay, so that's gone. Okay, and it's funny that I was just thinking this because I still, to this day, every once in a while, okay, because Ursa Major is large enough and stuff, you could still see some constellations and star systems and stuff from the Northern Hemisphere and the Southern, and vice versa. You could see some and stuff like that, but there are particular things that happen because of the different orientation and stuff. So, and I definitely thought about this. I mean, it's all matched up, and I said, well, the Big Dipper, okay, it turns upside down. So when you're looking at it, and when you can see some of it, when you can see it here in the Southern Hemisphere, it's upside down. It's upside down from the shape that it was when I was in the Northern Hemisphere. And occasionally, I remember feeling, I was like, oh wow, that's a little bit weird. Like I was just aware of it and stuff like that. Okay, so all right. So imagine that's your constellation, and here you are in the Northern Hemisphere. All right. The more as you go, all right, you're getting this effect. You understand? Okay, you're getting that effect, right? Just generally speaking. Now, this is on such a mass scale, and this is one of the problems of why in people who are sincerely debating and finding issues, why you're seeing a flat Earth possibility. Because I mentioned this a couple of times now, and you're starting to see why. Because there are flat behavior. Of course there is, but we need to understand the behavior as if it behaves as if it's flat doesn't necessarily mean that the property or the whole system is actually flat. Okay, it just has a flat behavior. And if you're thinking that doesn't, whoa, is there really a difference? Well, actually, sure there is. We understand that a sphere that is so large at any local point or whatever will have a flat behavior. In fact, there could be certain math or whatever that will work for flat, and it wouldn't necessarily work, or you'd need a whole bunch of you need a couple of equations or whatever adjustments to make it. And then you're going to say, oh yeah, you know what? All of that adjustments just proves that it's actually flat. No, because the reason that would be false is because when you move into a different relationship about something else, whether it be a little bit more in size or just something else, you might a flat behavior and a flat nature explanation might not work. You might need one for a sphere. You see? So trying to say it's flat no matter what runs you into problems. Trying to insist that it's going to work for a sphere will actually work, okay? But you may need a few translations, and you may need to add a few proper variables to account for that. Why? Because what you're trying to do, because you are dealing with an area that has flat property, that has a flat nature to it, even if it's just in our measuring tools and the way our measuring tools work. They're not totally exclusive from our senses and stuff, okay, since they are derived from us. So there are certain little, even when it's just a mental note, like mental notes that you make to yourself, they're saying, well, I can see that these railroad tracks converge in the distance, but they don't. So, okay, but even when you look in a telescope, okay, you may see the tracks separate, but even further down, at some point, even in the telescope's field of vision, they're going to meet somewhere, okay? So even with your equipment, you still need a few other variables, okay? So you're making that mental note, but there's more than just a mental note. If you were to take a snapshot of that image from the telescope, you would need to include in the formula how at every distance when the tracks converge at their degrees or whatever, okay, you would need to translate that into a degree of, adding to the actual parallel relationship between them. A correction, an adjustment. That's not proving that science is wrong. That's not proving that there's some kind of conspiracy, okay? That's reality, okay? So, all right. All right, yo. So you following me? So right? You see that? So as you move your angle, in theory, even though it's not so drastic as we're going to make it here, but we're going to show you the general theory of what's happening. You increase your angle, okay, to the constellation, so you should be able to see more of the side, technically speaking, right? If you're directly under it, you see directly under it. You don't really have good access to the sides of it, correct? So the more you go like this outwards, the more it goes like that, okay? The more your vision is seeing the side of it. So basically, if you were traveling away from me, okay, especially because we have the angle, the incline, elevation angle as well, okay? So you're going to see that tilt, right? We know this because we could see it happening. And we've done incredible math with also dividing up the sky into arcs, degrees, arcs, and arc second. It's brilliant. It works brilliantly, okay? So not only are we moving away, okay, but we're also moving away on the curvature. So, okay, so what happens is, and this is, you could get this in graphics, you get this in, you mess with all of these angles of rotation, right, and stuff. So as you're going like that now, you understand? Okay, so there's the equator, which is basically like it divides that middle point. It acts as like a horizon for that threshold between. So anything north of the equator, okay, and you're dealing with this, okay? Anything south of the equator, and it's going like that, okay? So when I got to the Southern Hemisphere and I looked at the Big Dipper, it was upside down to me. And that corresponds with a globe. There's absolutely no reason why it should go upside down for me on a flat Earth. No matter what, even if it was slanted. You can't. The slant would have to be in such a way as to actually start curving. In order to cross that threshold, to cross the equator horizon, and across that line, to have it like that. understand? So, here in the Southern Hemisphere, and it's tricky, because it can be tricky, because remember, if I point myself north here, I can see sky. It's not like, you see, you get this idea like, if I'm in the Southern Hemisphere, guys, and let's say a lot of my friends right now are in the Northern Hemisphere, it's not like if I wanted to face north, I would lay on the ground now, like thinking clever, and I would need to look straight to the ground. No, it's not like I would need to look straight through no, I can face north here and see sky. So that creates a lot of problems.
The following presentation is meant to stay basic and provide some introduction to the history and issues of early navigation of the sea, map making, and projecting a spherical topography onto a flat map. In this example, you are an early navigator of the sea. Let's say before the inventions and use of the sextant and also the chronometer. When you went navigating the world by sea, you recorded a landmass in the Northern Hemisphere and another mass of land toward the equator, and one more land in the Southern Hemisphere. Naturally, you recorded all these measurements on a flat piece of paper. You then provided the additional info, like the cardinal directions and the kind of celestial navigation you used, the sun, constellations, a grid. As others used your maps and charts, more definition and accuracy was confirmed, especially to the grid line values. When others navigated from the equator to the northern landmass, they may have agreed with the recorded size, but identified that you plotted it inaccurately. So it gets updated. But before it was updated, people who navigated from the northern to the southern had updated the southern. And yet, when navigating from the updated northern, it was confirmed that both the original and updated southern were inaccurate. So another update was provided. But while all that was happening, navigators from the northern and southern independently confirmed the equator landmass was plotted inaccurately. So the updates from the northern navigation claim it is actually over here, while the updates from the southern navigation claim it is this way. So far, this is what we now have. Now, it is most accurate to point out that the concepts, theories, and beliefs that the Earth was spherical have been around since BC. And sea navigation wasn't the only circumstance that needed a better model than the science for a flat Earth. Cosmology, geology, cartography, to name a few. And I'm not going to get into the amazing history of spherical understanding and confirmations. So here's what we figured out. We were taking a curved distance, a distance over a curve, and squashing it flat. So, as you can imagine, the land masses get distorted. Basically, if you preserve the proper shape of the continents onto a plane, a flat map, then the sizes distort. This map uses the famous Mercator projection, basically the world standard map. The angles and shapes are preserved, but size, area, distortion increases further from the equator. If you preserve the proper sizes, the area of the continents, then the shape distorts. This map uses the Malvida projection. The proportions of the area of the continents are accurate, but the shapes distort. So there were inconsistencies in early ocean navigation. Vessels certainly got lost, some crashed or became stuck in shallow coastline waters. But we continue to find evidence of successful navigation as well, often involving a good understanding of the celestial bodies. Notice the use of parallels and meridians. All these compass roses with straight lines are not rhumb lines or meridians. They are not longitude and latitude lines. They are particular points of empirical observations and compass bearing. So, imagine each compass rose point was where the navigator recorded a relative time, or event, or a known fixed position, and then recorded the moment of sunrise when the sun was peeking through the east horizon, the path of the sunrise, local noon, the point when the sun was directly overhead, the point as well as the path when the sun crossed over and was lowering, the sunset as the sun sunk below the horizon. The plane angle, in degrees, a degree of arc, is also recorded for all of this. With all these locations and their different angles and relationships to the sun, our ancestors knew it was not behaving like a flat surface at all. These records of observation played a big role in the accuracy of our ancestors' descriptions of the surface of the world. Navigators, astronomers, mathematicians, cartographers, and many others would collect as much info as possible and use it to reveal the truth. Acquiring an accurate map, chart, or other navigational instrument was quite beneficial to sea navigators. And obviously, so was being able to use them, or use them effectively. So paying or trading info to an astronomer in return for celestial observation techniques and demonstrations could be the difference between life and death at sea. Okay, so let's take a look at some celestial relationships and other basic values that helped early navigation. We have defined 4 cardinal directions for this place. And we notice the constant that the sun rises in the east and settles in the west. So, all the people on the east side see the new day's sun sooner than all the people in the west. The sun reaches its highest point at different times for different longitudes. For example, but everyone who shares the same meridian of longitude, which means they all have the same east-west location, but different north-south locations, will have the same highest point for the sun. While these other folks have a different angle. And it continues. A very peculiar thing happened when we took all those measurements and angles and plotted them on a surface. We didn't get an evenly spaced square grid. We got something that looked like this. But this is hardly arbitrary. Many of the location values and measurements are not interchangeable. Certain locations, areas, regions are unique, like having half a year of continuous daylight followed by half a year of continuous nighttime at the poles. So we also realize the Earth rotates around its own axis, and it's tilted, We realize the Earth orbits around the Sun too. I highly recommend taking some time to explore our history of navigation, both land and sea exploration. And notice how intricately related it is to the history of astronomy, survey science, cartology, to name a few. And of course, the sciences and markets of invention and production. For example, explore the history of the role ocean navigation played in advancing our ability to produce a device which can precisely maintain a measurement of time. It's a fantastic story of engineering, urgency of deadlines and necessity, as well as prestige and financial reward. Plus politics and foul play.
Here in the Southern Hemisphere, no matter how powerful my telescope is, no matter whatever I do, I can point it north right here in the Southern Hemisphere. And no matter what I do or whatever, it is not going to find the North Star. It is not going to find the North Pole, no matter what.